Okay, so today we're going to continue with integration by substitution. So we're just evaluating these integrals. Most of them we're going to have to do U-substitution, but there is going to be some kind of, I don't want to say trick because then you think that I'm trying to trick you, but it's just some kind of nuance, something that's a little bit different. Okay? So in this case, number one, again, when we look at U-substitution, okay, we're looking for a function and its derivative. Okay, so like on the top, we see e to the x or 2x e to the x squared, right? And right there, I see that's a function inside of a function. But on the bottom, I also have the same thing. Okay, now we've done a problem very similar to this where it was 2x e to the x squared, and we had to do U-substitution on that to find its antiderivative. Okay, this is kind of, I want to say, like a special case. Okay, so before we picked x squared when we did 2x e to the x, we picked x squared as u, and we used 2x as our dx. But this one's going to be a little different because now I have 2 e to the x's in the same problem. Okay, so what I'm going to do here is I'm going to say, okay, I'm going to pick u to be e to the x squared, like this. So that when I find du, I'm going to have to do chain rule. So I get 2x e to the x squared dx. Okay. So now I can see that this right here, this is du, and this right here is u. So we basically get the integration of du over u, like that. Or if you want to write it, you can write it as the integration of 1 over u du. Okay? But basically, what we have here is we have the antiderivative is going to be the natural log, because the antiderivative of 1 over u is going to be ln of u plus c. Okay? So, and then of course we plug in u at the end, so we get the natural log of e to the x squared plus c. Okay? And that's our answer. Now, technically we're not done simplifying. If you remember your logarithm properties, ln and e are inverses, so you're just left with x squared plus c. And that's actually your final answer. If you had looked at it at the beginning, you would have seen you've got e to the x squared divides out with e to the x squared, which just leaves you with 2x. So I just wanted to show you that you need to be looking out for these problems where you see this integration going on. As the bottom my u, the entire bottom my u, and the top the derivative of whatever that is. And that's signaling to you that it is in fact a natural log antiderivative. Because we know we've done chain rule, and the derivative rule for the natural log is d over dx of ln of u is du over u. We've been using that in the derivative. Now you got to start recognizing it the other way to find the antiderivative. Okay? So that's just one of those where you got to look and see, do you have the derivative over the actual function? Okay? All right. This one's a common problem that they give, where they expect you to be able to split this apart. So the first thing I'm going to do here is actually rewrite it as cosine of the natural log of x times 1 over x dx. So what I've done here is basically it's that whole idea of dividing by something is the same thing as multiplying by its reciprocal. Or you can think of it as pulling apart two fractions, because when you multiply fractions, you multiply straight across. So I can actually pull those two things apart to make it easier on myself. So that makes it easier because I know my u is going to be the natural log of x, and the derivative of that, the derivative of ln x is 1 over x dx. And this would have been harder to see, this du being 1 over x dx, if you had it in its original form here. Because you would have been like, oh, there's just an x on the bottom. I don't have 1 over x. But when you split it apart, you very easily see this. Okay, and this is something that they like to do. So that is my du, and that's my u. So when I rewrite, I get the integral of cosine of u du, and the antiderivative of cosine u is sine u plus c. And at the last part, we plug back in our u, so we get sine ln x plus c, and that's our antiderivative. Okay. So really easy, there's just little things that algebra things that we got to think about before we get started with our substitution. And then our last one for today is actually pulling together two pieces that we've done the last couple of days. Okay? So again, this is a definite integral this time, and I've got x times the square root of 2 minus x. So what we're going to do is, of course, u has got to be the 2 minus x on the inside, which means du is negative 1 dx, or negative du equals dx. So that's what we're going to use there. But again, this is one of those problems like we did yesterday where we've got that extra x hanging around. So in this case, we have to solve my original in terms of x. So basically, I'm going to move the x over, make it positive, equals 2 minus u. So x equals 2 minus u. Now, I do my substitution. So I get x is 2 minus u. This is u to the 1/2 times negative du. Okay? Now there's one last thing that I want to do. I want to change my upper and my lower limits. Okay? Because I want everything in terms of u. So I'm going to come over here and use this and say, okay, what's u when I plug in 1 for x? Well, that's going to be 2 minus 1, which is 1. And then u when I plug in 2, so you plug it in and you get 2 minus 2, which is 0. Okay? So my new lower limit is going to be 1, and my new upper limit is going to be 0. Now, if you notice our limits are backwards, so it's going from 1 to 0, it's supposed to go from the lower number to the higher number. So we're going to reverse the limits, which is going to make this negative go away for us. So we end up from 0 to 1, and then distribute in your u. So you get 2u to the 1/2 minus u to the 3/2 du. Okay, so I did a couple steps at the same time. All right, so now we're going to evaluate my definite integral. So we take the antiderivative. So this is going to be 2u to the 3 halves divided by 3 halves minus u to the 5 halves divided by 5 halves. And then we evaluate it from 0 to 1. Okay? Then we're going to simplify this, though, a little bit more, so it makes it easier. Dividing by 3 halves, so this ends up being 4/3 u to the 3 halves minus 2/5 u to the 5 halves from 0 to 1. And this makes it really easy to evaluate. Plug in 1, so you get 4/3 times 1 minus 2/5 times 1 minus 0. So you get common denominators. So this is going to be 20 over 15 minus 6 over 15, which ends up being 14 over 15, which is your answer. Okay? So this one here, there's a lot of algebra. Okay? And actually, if you look at this, the entirety of this problem, if you look at all of this problem together, the only calculus in this entire problem is basically going from this step to that step. This right here is the only calculus, taking the antiderivative. All the rest of it, algebra. And that's basically what happens in calculus, is that when you have weak algebra skills, it causes a compound problem, because the calculus is the easy part. And I've always told my students that, and they look at me like I'm crazy. But when you look at this problem, you can obviously see it's not the calculus here that was easy. Adding 1 and dividing by that number, that's the easy part. It's getting it to a form that we can actually do that. All that algebra we had to do to get to that point is what makes this problem really difficult. And then, of course, the fractions, which I know nobody likes.